Have you ever wondered how light behaves in a black hole and what happens inside it? To understand it, we have to start from the beginning. Black holes can form in different ways. One of these is the collapse of a star with a mass of at least 20 times that of the Sun. The star, once its fuel has run out, is crushed by the force of gravity. This process is called a supernova, in which the outer layers are expelled into space, while the inner layers collapse, deforming spacetime. This deformation tends to infinity at a point called a singularity. This is how a black hole is formed. That is, a black sphere delimited by the event horizon beyond which no event can influence an external observer. An accretion disk orbits around it. The event horizon coincides with the Schwarzschild radius, a characteristic radius of each object with mass that cannot be crossed by matter and electromagnetic waves, such as light. A non-rotating black hole with no electric charge, however, appears much larger than this measurement, by 2.6 times. To explain why, we need to study the behavior of light in a black hole. For simplicity, I made a black hole 2D and divided it into 3 concentric circles. The innermost, black one, represents the event horizon, and at its center is the singularity. On the circumference of the intermediate dark gray one, the light orbits around the black hole, while the outermost circle corresponds to what we see as a black sphere. To understand this, let's simulate 11 photons, 9 of which are directed towards the intermediate interior and 1 on the circumference, while the remaining is directed towards the circumference of the outermost circle. We note that the closer the photons are to the event horizon, the slower they move. Furthermore, the photon on the circle of the intermediate circumference has enough speed to remain in a circular orbit. If we trace their path, we notice that the one on the outermost circumference has grazed the intermediate circumference and managed to escape, while if we extend the path of all the photons directed towards the innermost areas, we obtain spirals that converge in the center, which however will never be completely traversed. A sort of shadow is thus formed, which corresponds to the event horizon seen in its entirety from every angle. The accretion disk has a minimum orbit of 3 Schwarzschild radii, while light orbits at 1.5 Schwarzschild radii. If we somehow increased its speed, we would never see the center of the black hole, but would only decrease the size of the radius of the latter. One last thing. Since we see the accretion disk from a random angle, it does not appear flat but curved around the black hole. This is because the curvature of spacetime modifies the trajectory of light even outside the black hole, allowing us to also see what is behind it.